Hi, in this video, we'll be continuing on studying statistics, and before we get into the main bulk of statistics, there are some distributions that are commonly used when we study statistics. So the first one we have already seen from the last lesson on how to get its PDF and CDF. That is, if you take a standard normal and you square it, this distribution is known as the chi-squared distribution with 1 degree of freedom. It can also be a special case of the gamma distribution, but we like to treat it as a square of a normal. And the definition of a chi-squared with n degrees of freedom is taking independent chi-squared distributions of 1 degree and adding them n times together. So this is the definition of a chi-squared distribution. And so why is it a special case of the gamma? So here's a preview of what a gamma distribution looks like. So this is a gamma density, and a chi-squared degree 1 is when you just put in half here, then everything forms up nicely. So we also note that the sum of independent gammas have the same lambda value, and therefore because chi-squared is gamma, adding them together will have the same lambda. So this allows us to find the expectation to be n, and the variance is 2n. And so to indicate that v follows a chi-squared, we just put v tilde chi, which is like this curly cross, n squared. And if u and v are both chi-squared, then when you add them together, it is still chi-squared. Just imagine you have u1 all the way to plus um plus u1 plus all the way to un. This can be now changed to n plus 1, or this is just n plus n. So it's just chi-squared n plus n degrees of freedom. And by definition now, we can next form another distribution known as the T distribution. And so we have the standard normal and a chi-squared distribution with n degrees of freedom, and they are independent. Then we say that the distribution of z over square root of u over n is a T distribution. And the density function is as follows, which is very complicated looking. But you can prove it using a standard method, and the details are left in the textbook. So, but the more important thing is that what we want is that from this distribution, we understand that it is symmetric, about 0. And as the degrees of freedom approaches infinity, meaning n become very large, then this actually becomes the standard normal distribution. So it's a very good approximation. So this is sometimes a more appropriate use compared to the standard normal, because standard normal you need to know the distribution, but for T distribution you don't really need to know what the variance is. So the variance can be unknown, but you can use the T distribution to help you for hypothesis testing or any other statistic test. That's why we like the T distribution a lot. And the F distribution is when you take 2 chi-squared, you divide by the degree of freedom, and you divide it again together, then that's called a F distribution. Again, the density function is very complicated, and the details are left in the textbook for your own reading. What's important is to know for F distribution is that the expectation exists and equals to n over n minus 2. And from the definition of the T and F distribution, it follows that the square of a T distribution actually follows the F distribution. So these are the 3 most common distributions that we like: the chi-squared, This will be especially useful in when we do a test for whether two models are appropriately good for one another. And a t-distribution is like a normal, so you can test like the mean, but sometimes your variance is unknown, so you rather use a t-distribution. So moving on, we'll move on now to what is known as a sample mean. And so if let's say you got n independent normal random variables, then then you take a sample. Then this is just a sample because your population is the whole everyone. Then you just take n people, so it becomes a sample. And this sample will also be from this normal distribution. And so you can actually find the joint and marginal distributions of these. So when you take this normal, you add them all up, this becomes like some new random variable. And what is this distribution we'll now take note of. So this is known as the sample mean and sample variance, which we use this symbol to denote. And because x bar is a linear combination of normal, it will still be normally distributed, and this is the expectation and variance of x bar. And so let's just examine x bar first in greater detail. So the random variable of the sample mean and the vector of the random variable, these are independent. So what does it mean? It means you have the sample mean vector, which is like the x, you have the sample mean, which is like some mu after adding everything, and then you got the random vector, which is this. They are independent. Theorem left is just quite algebraic, but to prove they are independent, you just show that the distributions, the joint distribution equals to the marginal times marginal. So basically that's how you're going to do it lah. But it's very algebraic, and I'll omit the proof in this part. But because if you already know this is independent, then it becomes very clear that x bar and this variance is also independently distributed, because s squared is a function of this vector. Because remember, what's s squared? S squared is over here xi minus x bar, and here is xi minus x bar. So it's a function of this vector. So, and this vector is already independent of x bar, so of course s squared is also independent. So it's the corollary that is more important, which is the x bar and s squared are independently distributed. And with that, we can see that the distribution of n minus 1 times s squared over sigma squared is a chi distribution of n minus 1 degree of freedom. How do we know? It's because remember we said that z squared is chi distribution of degree of freedom 1. By definition, this would then be a chi distribution of degree n, and then you can rewrite this into the following form. And expanding the square, now you use the fact that xi minus x bar holding sum is 0. We obtain the following result. And by the above corollary, we know that this and this are independently distributed. So what does that mean? That means because this is a function of x bar and this is a function of s squared, so these are independently distributed. The moments generating function will equal to one another. And since w and v, both this and this follow chi, this is chi squared, and this is chi and a chi squared. This is standard normal squared, so it's chi squared. you can just take the moment generating function of W divided by V to get the U, which is actually what you want, and you obtain this. And you actually realize that there is a chi-square distribution n minus 1 degree of freedom. So if you want to brush up on what is a moment generating function, you can check out my video in the probability series where I talk about it. And a corollary of this is finally we get to see that when you normalize the sample mean x bar minus mu over s over square n, this s is your sample variance. So instead of using population variance, which sometimes can be unknown, we have the sample variance. We will actually see that it follows t distribution instead. That's why we use t distribution instead of normal. And the reason is very simple. It's just this can be converted into some normal over s squared, and we already know s squared is chi. So from earlier, that's our definition of a t distribution. So these are a very quick video and give you a preview and understanding of what is chi-squared, what is t, and what is f distribution, so that we can use these distributions later on when we do statistical testing. And we introduce now what is a sample mean and sample variance, and what type of distributions do, and why do these type of distribution follow t or not. So this will help us later on, especially in hypothesis testing. You recognize this again. So that's all for this video. I hope you have enjoyed it. Please like, share, and subscribe, and I'll catch you in the next video. See you again. Bye.